know how you can that risk free. But of course, premium, that's the second part, right? We need to adjust risk premium given the characteristics of the operation. So that brings a number of problems, such as what do we understand by risk, how this risk premium can be tailored and adjusted specifically to that amount of risk. And we have different theoretical models and approaches because this question is particularly relevant in the context of the equity markets. So we're going to review the main ideas underlying the determination of the risk premium that go to the CAPM and then the generalizations of the CAPM, the formal French model. I'm going to talk also in this chapter about the stylized features of the stock returns. We already know them. We sort of make these, we saw these ideas empirically. We're going to sort of simply survey these ideas because we need to underline some of them. So we're going to sort of review them. Okay, notation is going to be very simple as well. We know them by definition. We're going to work with returns. So we will have one period returns. So that's the end of period, simple return. And then I'm going to use some mathematical notation here, which is going to be this bold letter to mean vectors and matrices. In the world of the portfolio, we need to think in terms of multi-dimensional. We will have a portfolio made out of 5 assets, and then the expected return will be an array 5 by 1, having 5 elements, each one with the expected return of each of the individual assets. So we will work with matrices and the standard notation in mathematics in order to differentiate of a scalar is bold letter for the array, so vector or matrix, and just regular letter for the scalar. A row in mathematics is this, a vector in mathematics is a row vector. By default, this is the position. When you tell me this is a vector of returns, I visualize a column vector. And that would be X, right, for instance, with this capital letter. And if I want to transpose this vector, I want to make it into a row vector, I want to make this column vector into a row vector, then we use the transpose operation. All right, you are going to see this notation because algebra helps me a lot in order to characterize certain things. I recommend you a couple of books. These 2 books, I chose them because they are available in the internet. You click on in the hyperlink, you will get access to the PDF book. It's not me who are giving the PDF. I'm just giving you the address that someone, for some reason, put that in there. And they are very good books. The Salmon Technical is, I mean, it will be there for some while. I don't know, maybe next year they are not there. So,
we have to take advantage of it.
exactly. It's not my book, it's just a, you type the name of the book and PDF, you get the same access. So they are very good books. One related to financial modeling, which is what we are going to do, and another sort of general book, quantitative investment analysis, is a CFA book, and it's something that I strongly recommend you because it's written for people in finance, for other people in finance. So technicalities are there, but it's not that much as you're going to see in econometric books, which is much more, tough, a heavy metal, right? In ADDI, you're going to find also certain material. We have this case starting proof, which is a kind of macro that we can run to do regression analysis. I will use that later in the context where we estimate, when we apply the CAPM and when we apply the Fama-French model to do regressions. You have other tools. You have data analysis, but this is much more sophisticated. This has been programmed by someone, and I hack it. That's why I call it improve. It's a kind of variant that I add in certain functionalities, but I give full credit to the guy that programmed that originally. And that's a guy, is another professor from Kellogg University. So in case you may like to see the original one, that's where you can find the original file. He says, this is, you can use it as long as you don't modify anything. That was the very first thing that I did. I changed it and I said, it's so good, this is brilliant. I mean, you will see when we use it. Bad news, it will not work for the Mac users. So it's an option for everybody else, but the Mac user will not work for you guys. I'm sorry. It used to work, two versions, but like 6 years ago, Mac did something, they changed something, and it's no longer working. So you'll miss it. And then we have data. We will work with certain data and examples and everything that is on ad. Okay? So what we are doing in this chapter is essentially review the theory, the modern, people call it the modern theory of finance, that started with a very super well-known paper, a Markovitch paper, published in the Journal of Finance, pretty much 70 years ago. They call it modern finance, but it's really the beginning of modern finance as we understand it. Meaning, at that time, it's what you see, you have Arrow, you have all these people in economics doing quantitative analysis and bringing mathematical arguments into the decisions. So this guy made something that at the moment looked like a very simplistic. People sort of blamed us, saying, so you are just working with meaning and balances, but it took over. And it became super popular. And from the beginning of that, that was the seed of something that became bigger and bigger. So we have reviewed this theory in this chapter. And of course, very applied, in the same spirit as chapter 1. Don't expect too much theory. That's the beauty of finance, is that it's an applied field. So we are going to work with Excel much more than we did in the first chapter. Okay? Let me review a couple of things of returns, of stock returns. The things that we call stylized features. There are quite a few, but I'm going to just mention 4. Things that we already know, by the way. Returns tend to yield a positive return. If I compute the average return, that's going to be a positive value bigger than the risk-free rate. And that's another symptom of risk aversion. Whenever I see historical prices and historical returns of risky assets, I tend to see larger returns in more risky assets. Then returns we already discussed are not normal because we have skewness and stress kurtosis. We have extreme values, and we saw that in the first workshop that we did. There is another pattern which is super important in returns, which is volatility clustering. Stock returns are uncorrelated, but they are not independent. People tend to mix these two things. Something that has zero correlation is uncorrelated, but not necessarily independent. And the fact that it's not independent helps us to estimate or to predict other things that the return is safe. Because the return is uncorrelated, it is very hard to predict future returns. But because returns are not independent, we can predict other features of the time series of return, such as volatility. There are patterns of volatility that we already mentioned, in which periods of high volatility tend to be followed by periods of high volatility, whereas periods of low volatility tend to be followed by low volatility. We will mention that. And finally, we have cross-sectional positive correlations. Stocks are uncorrelated over time, but when you analyze the correlation of different stocks across what we call cross-sectional dimension, you see correlations. And that tells us that there must be exposures to the same risk factors. The returns are correlated because they can move as a consequence of being exposed to the same sort of risk factors as we discussed, right, in the SER model. Okay, let me just give you a few pictures of what I'm saying. There is a risk-return trade-off. Stocks that are more profitable, that generate greater expected returns, are more volatile. If you want to have greater performance, you need to take on greater risk. That's what we call the risk-return trade-off. And here you have, over pretty much 100 years, the mean variance of different classes of assets, and you see this pattern. More expected return, which is something that I love, comes at the price of greater volatility, greater uncertainty that I dislike. So I need to be confronted with this thing. If I want to achieve greater returns, such as cryptocurrency, then I need to be exposed to, nightmares.
Can you use it again, like number 3 of the proof slide?
Number 3, I'm gonna go there right now. Number 2, returns are not normally distributed, and this is something that was clear the other day, right? We were working with daily returns, Here you have daily returns over 45 years in the S&P 500. If returns were normally distributed, you will have something fitted by this Gaussian distribution. In reality, the distribution of returns has something which is much more spiky, meaning there is much more concentrated of returns around zero than expected under the normal, and then we have a propensity to find some values over here, very early to core, and even more extreme values over there. If we analyze the time series of returns, we can recognize those extreme values. The most extreme values in that sample, starting from the 80s, is something that happened in the 87, and that thing is called the Black Monday. I don't know if you guys have heard of that. It's been the largest crash in the stock market ever. One day, in one single day, the market lost 23%. One single day. And there is no why. Everyone was saying, what is the hell, what is going on? And the news was, there is no news. You see, the next extreme movements are concentrated in the financial crisis in this period and during the COVID. So you see, at least you understand where it's going. There is a crash. The market is crashing. Investors are very, very, very worried. I understand uncertainty reflected in price changes. There, nothing particularly happened. People get scared, and it was a kind of, snowball that was 23% in a single day. This is far from being normal, but it may happen. And if it happened in the past, it may happen in the future. It didn't happen again, by the way, because the markets are cheating. As soon as the market is losing too much, we have what is called circuit breakers, which essentially is we take the stock out of trading. That's why you don't see those big falls after this crash. Not because that couldn't happen, but because the market is preventing that from happening. They stop the trading and they say, okay, tomorrow we open again. Just wait until people is a little bit, easy, and see what happens tomorrow. And maybe tomorrow the process repeats itself, but then they cut the trading again. All right. Then we have this dependence number 3 that you mentioned before. This is the autocorrelation function. Autocorrelation function is analyzing how returns commute together. I would like to analyze how the return commutes with the return in the previous day. We call that thing the first order autocorrelation. How return correlates with 2 days ago. This is the second order autocorrelation. And we can construct these correlations and to make a plot, which is the autocorrelation function, which you have it there. You have it there. Those are bands which are 95% significant bands. Everything that is within the bands is not statistically significantly different from 0. And 100 correlations, like I have there, means that we should get something like 5 correlations which are out of the bands just by pure, luck. So what we observe is a first order correlation, because this is an index, this is the S&P 500 index, and we tend to observe a very mild correlation, which is an artifact. It's caused by the fact that the stocks of which this index is composed of are not traded exactly at the same time. We are collecting the closing prices, but they don't trade exactly at the same moment in time. And that creates a false impression of dependence. You will not be able to exploit this seemingly significant correlation because A is very tiny, it's just of the order of 7%. Secondly, it's spurious, it's an artifact. But if we examine the correlations of the absolute value of returns, not returns, the absolute value of returns, meaning I'm looking not about how much we made, gain or loss, but how intense was the movement. Big returns, either positive or negative, create a big absolute return. Small returns, either positive or negative, create a small absolute return. There, I observe a massive structure of correlation. That tells you that you cannot predict what the return will be next day, but you can tell if it is going to be a large return or a low return. You understand what I'm saying? You don't know if it's going to be a positive return or a negative return. So that prevents you from exploiting in your benefit, making, for instance, an interest portfolio. But you can tell if tomorrow it's going to be a kind of epic day or a volatile day or an easy day.
Well, you said like returns are uncorrelated together, but not independent.
Because of this reason, if returns were independent, if you have a truly independent series, independence means that the return at IT is not generated in any way, it has no dependence at all in any form with what happened in the previous day. So you should not observe correlation at the returns, but you should not observe correlation in any other function of the return. So the fact that we observe correlation when we take absolute values of return tells me that returns are not independent. They are uncorrelated though. Let me remark that idea. If we have zero correlation, then the series is said to be uncorrelated, but not necessarily independent. Now, if you have independence, then independence implies zero correlation. So one thing implies the other, but the other way is not necessarily true. Independence is the strongest condition. If you have independence, so like a throwaway coin, what you lottery games, what you did last year will not help you in the future. So there is no transformation of that information that can help you to forecast the future. Absolute values, whatever you want. There is no dependence that you can exploit.
So,
But
no, I was going to ask if this happens because we can have the correlation is linear, but we can have like non-linear relations.
it's absolutely. Correlation is a measure of linear dependence. So all what you are saying is there is no linear dependence in the returns. But maybe another form of dependence, such as dependence between the absolute values, non-linear dependence. Indeed, good point. Very good point. Okay? And then as we say, we have returns that exceed correlation, cross correlation, not correlation over time, but cross correlation with other assets. And why this could be explained? Because assets, so let's say the return of asset I, the return of asset J, are driven by the same underlying factors. So we have risk factors that move everything, and then when we examine the returns which are caused by other factors, we realize that they are the consequence of some hidden factors of a latent variable that must underlie. And of course, there is a big question in finance upon which are those factors. Identifying those factors will help us to say something about the dependence of returns, right? And to, for instance, exploit that in portfolios. Which are the factors who drive the return? This is a big question in asset pricing, in empirical finance. And well, to make things even funnier, you may think, okay, so assets are correlated, right? Yes, they are correlated, and they are, those correlations are time varying. And this is, of course, something that needs to be true in practice, in real life. Things are not static in real life. Everything moves in the markets. So that means that equity risk premium, betas, covariances, variances are non-stationary. They change over time. And that prevents us from using very long time series of data because things are moving. If something is moving, I want the most recent information to target it, to pick it up. If I take a very long time series, I'm going to get the picture of something in the past, not right now.
Like going back to what returns, what you explained that are independent and correlated, like returns therefore are not independent.
Returns are not independent.
So they are dependent.
They are dependent.
Right.
They have a dependency in the volatility, the variable. It's like I just said something like, let's put it this way. A model for us returns, right? The return, the excess of return, the risk-adjusted return would be something like let's put it, this is not true, right? Normal, center at 0, so you may get something just because you're lucky or not, like a Monte Carlo analysis. But now the point is the variance of this distribution is time variable. You will not get you don't have the ability to forecast the future return, but this variance is, for instance, going in a way something like this. There's a pattern dependence on the variance. In this, imagine a Monte Carlo simulation like we did the other day. If I have today a large variance, tomorrow, that large variance is going to be more likely to go. So you don't create one new return independently of the other. And that's important, of course. That's very important because if you ask for independence, that model that you have is not tracking reality. And if you want to forecast returns, you want to do something with reality. You can exploit economic models not to forecast returns, which would be the best goal possible, but you can forecast volatility. And that will give you an advantage of people that are not aware of that or don't have that technology.
And we say that they are uncorrelated because we cannot see a trend. No? There is no pattern. It's like put it this way. Put it this way. Imagine that there is three. You observe the market falling down 3 consecutive days. Monday was a bad day. Tuesday is a bad day. Wednesday is a bad day. What would you expect the next day? To be a good or to be a bad? Bad day. Imagine that stock prices returns are negative 3 consecutive days. 3 bad days in a row. What do you expect in the 4th day? Bad, good? Depending on what you consider.
Surprise, doesn't matter. You will get just like imagine you throw a dice and you get 3 consecutive fives. And my question is, what is the chance to get a 4th 5? And the answer is the same
as before.
Because there is independence. So this is what happens with returns. You observe prices falling down, and because there is no dependence in the return, that information will not help you.
But can we say they are dependent?
In volatility, the variability. You tell me, I don't know if tomorrow is going to be a good day or a bad day, but today everyone is crazy in the market. Everyone is selling a lot, and prices are moving. How's going to be the session tomorrow? Like this one. Tomorrow can be a day in which you will make a lot of money or you lose a lot of money. I cannot say if it's going to be a winning day or a losing day, but I can tell you, if the market today is hectic, tomorrow the more likely scenario is volatility as well.
And I had a question because I've heard both things that, for example, some people say that really big data sets can maybe capture some features like really long-term seasonalities.
Right.
But other people say like you have nothing to do with 1980 prices of Apple stock, so what's something?
There must be something there. The point is that it's like put it this way, long-hanging fruit is not available. There may be something, but it's on the top of the tree. You are going to have to climb up, you are going to have to sweat in order to get that profit. So this is there, but it's going to be expensive and hard to get it. For most people, it's something that we cannot afford. You need to have strong resources in order to get rid of tiny margins. And they do that. People can profit from that. But it's not something like it's like a crypto. When you say crypto, the chances to get a lot of money in the crypto market, when compared when the market started, how would you say it's right now? The same, much lower. Because the market has improved efficiency. Now a lot of people are there. And those people prevent you from getting those opportunities in efficient markets. In very efficient markets, and stock markets people say are efficiently inefficient. Meaning, of course, there must be something. Otherwise, people, why investing money? Is spending money in Bloomberg because it needs to pay off somehow. but that's gonna be a tough investment. It's not something that comes, easy. Okay, and some people believe, oh, I have this method, I see this shoulder, head, shoulder, it's time to buy. Come on,
I've been there.
come on. I am taking this course that says, come on. It's not like that.
So I understand the whole, we talked about the diversifying portfolios and that's why we diversify across different assets. The question is, you want to mention like if you have today volatility, now might be an indicator, tomorrow we also have it's not like every single day is
Independence. There is no independence. That's the point. That's what I'm saying. There is no independence from one day to another. But you no
And it's like
independence.
if today we have a volatile day, that's even tomorrow it will be the same.
Right. Okay. There is no independence. It's not just like a Monte Carlo. As we get those normal things, every cell was different from the other. Not any connection. There is some dependence, but in volatility, not in the level. It's like that. You create a path of dependence that goes in volatility. And that's reflected in periods of low volatility followed by low volatility. Periods of high volatility followed by periods of high volatility.
Okay, so it might be an event if today is volatile, there's going to be a chance.
More likely scenario is volatile as well. That's breaking independence. Okay? If returns were independent, we will not observe that pattern. We should observe something like this. And we don't observe this type thing. We observe these clusters. That's breaking independence. Okay, guys? So this last graph is called rolling window. Rolling window means that I take a window. So in this case, I'm taking 60 months of returns from the S&P 500, the US market, and the FTSE, which is the UK's market. 50 returns, 5 years making 60 monthly observations. And I compute the correlation of contemporaneous correlation between the US and the UK. And then I repeat this experiment, given one step further. So I move the window one period in the future, I gain a new observation, but then I remove the oldest one. I keep constant the window at 60 observations, and I'm moving this window one period, complete new correlation, one period, new correlation, and this is the graph of correlation. So this is time varying, clearly. There are periods of correlation between the US and the UK, and you see that correlation is very high overall, right? The overall correlation is about 70%. So if you want to diversify by investing in the US and the UK, that's not going to work. It's a strong correlation between the two markets. That's global integration. But to make things even funnier, the correlation increases during periods of crisis. The argument to diversify, which is trying to find a way from crisis, is going to be very complicated because assets tend to behave and move together, particularly during bad times. And every time more stronger is really stronger. We have moved from the 80s onward in something that is market integration. It doesn't matter whether you are living in Europe, it is very easy for you to buy stocks in the US. It's very easy and simple. And 40 years ago, it wasn't so easy, right? So we have strongest integration between markets. All right, so what is the mean variance analysis? The mean variance is a normative model. Normative model means that this guy cared about how investment should be done. That's the difference between, but this is the point of a normative model. And there are three distinctive assumptions in this model. It's one period. So this is very classic, we've seen several times already. You make decisions at the beginning of period T, right? And then one period later, and that could be 40 years or 1 month, depending on your horizon, or your investment horizon, the decision, the results of your decision realize. And of course, the outcome is uncertain. So we have randomness, and returns are going to be treated as random. So we have one period model with uncertainty. We are going to consider an investment university which is formed only by risky assets. Markovich lost something massively important in this analysis he made. It was the first time he did it, and he just considered that was a big error. I only consider investments in the stock market. So we will consider investment made of K stocks. And then investors are risk averse, which is of course something that makes sense. We have already discussed this idea. And when they choose different portfolios, and this is the particularity of this analysis, they only care about the mean and the variance. They like the mean, so the greater the expected return, the better, and they dislike variance as a measure of dispersion, as a measure of risk. Now, we may discuss whether this is true or not, whether this is accurate, this is sound or not, but this is the mean variance analysis because of this characteristic. Markovich analysis is called the mean variance setting because investors only care about mean and variance. And of course, there is a lot to discuss about this critical assumption he made. All right? When you care about mean variance, you can plot the results from your investment in this plot. I can characterize the result from my investment by characterizing how much I get on average in this axis. So this is mean, and here I characterize the variance of my return. And you make different portfolios, and this new portfolio, each of them will produce a expected return. We have a mean and we have a variance. And if you plot all these combinations in the mean variance setting, appears a very distinctive feature, a very distinctive graph like this one. Not exactly straight like that one, but this idea of the investments that yield the better returns, something that we all will love, and at the same time, the investments with greater variance. So there is a trade-off. This is risk aversion. This is another manifestation of risk aversion. But the guy noticed something very important. If you consider each of those portfolios the investment of a different individual all over the stock market, you see immediately that just a few of them are good investors. Most of them are making bad decisions, and bad decisions understood as decisions that could be improved.
Not really efficient from here.
For someone with a volatility 8%, we observe along this line all these portfolios. The best one is this guy. The one that for a level of volatility, 18%, reaches the maximum expected return possible. All of the portfolios are said to be dominating, are said to be inefficient. You make a decision, creates certain return, it could be good, but not the best possible. And this portfolio is said to be inefficient. And the same thing if we look at the return, right? Look at this 13% expected return. All these guys along this line are making portfolios that yield 13% return. But only this guy here has the minimum variance possible. All the other guys are making portfolios with the same expected return, but suffer greater variability. So those portfolios are inferior, are dominating, are inefficient. And the point of Markovich was, I'm going to give you the formulas and the methodology to make sure that given your expected returns and your variance, you will end up in this envelope that we call the efficient protein. The first time someone cared about this, bringing quantitative analysis in decision making in the stock market. Right now it looks like a very simple. At the time it wasn't. It comes in the 50s when the theory optimization was put forward by the mathematicians. The mathematics behind that we need to resort to do the optimization were put forward in this time. So Markovich brought, oh, look what these mathematicians are doing. Oh, this formula is similar to someone in the market. There's like an open idea. Why not crossing the two things? This is what we do. The PhD students, most of the time, this is what we do. Idea A, idea B, clean, A plus B, my paper. That's it. Okay guys, so this is what we're gonna do. Alright, so what is the idea of mixing things, just caring about mean variance, is something that we can sort of think that is okay. Individuals that only care about mean and variance, makes sense? We have discussed that investors are von Neumann expected utility maximizers. You want to maximize expected utility. So, how can we consider this idea? Just caring about mean and variance with the idea of maximizing expected utility. Well, one possibility is the quadratic utility function. The quadratic utility function only cares about wealth and wealth squared. So if you take the expectation of this utility, you end up with something that depends on the expected return and the variance of the return, the expected wealth and the variance of wealth. So that's a way to sort of consider these two seemingly unrelated ideas. Problem: people don't have quadratic utility functions. We discussed that in the first chapter. The quadratic utility function is not a good representation of how people make decisions. You have something like this, right? And then quadratic utility function means that you reach some point, and then quadratic means falling down. No way, no, that's not a good idea. Next idea to explain that thing. Next idea to consider expected utility maximizer, we just care about the mean and the variance, is to believe that a guy is making decisions with returns that are normally distributed. Because if returns are normally distributed, and we have, for instance, a Cara utility function, then expected utility only will depend on expected wealth and variance of wealth. Why? Because the normal is fully characterized by the mean and the variance. So another possibility is thinking that returns are normally distributed. And the problem is, as we've seen in the established features, you cannot take the idea that returns are normally distributed. So the final position that Markovich in a later paper tried to sort of explain is that what if you have a reverse utility function, and that can be approximated reasonably well with a second order Taylor expansion, which is a kind of desperate argument, right? Maybe any other utility function, other things may matter, but the most important thing for you is mean and variance. Nowadays, 70 years later, we know that investors care a lot about, for instance, skewness. Investors care a lot about the skewness. So the mean variance analysis is like a, okay, first approach, but not the definite approach. And people are making more complicated algorithms in which this skewness and kurtosis and other features of the returns are brought into the analysis. Okay, but that's high tech, that's for quantitative signature courses in masters in quantitative finance. So just I mentioned this. Okay, so let me present you our framework. We will have k assets, k risky assets. So we have a vector of returns that can be characterized by an array, a column vector, in which we will have, for instance, if we have 5 assets, we will have a 5 by 1 entries, each one with the expected return of each of the assets. And that's going to be the expected mean vector. And then we're going to have a matrix, which is a variance covariance matrix. On the diagonal, we have individual variances of each of the k assets, and in the off-diagonal elements, we have covariances. And both variances are important from a unilateral perspective, but also covariances are super important. If I buy an asset and it correlates with another asset, they can move together, that covariance is important in the mean variance analysis. So in the Markovich setting, we just need 2 ingredients. You need to come up with this vector and with this covariance matrix. How you determine those things is something that Markovich never dared to say. It's your problem. If you come up with good estimate of expected return, your portfolios are going to be super good. If you do a poor job on that, I'm sorry, guess what? Garbage in, garbage out. It's just like that. That's the difference between a good portfolio manager and a bad portfolio manager. They both will use the same techniques, the same portfolio management techniques, but the good manager is able to come up with better ingredients somehow than the bad man. Alright? Our point in this analysis is to determine a vector, which is the composition of the portfolio. So let's say that we have 5 assets. I don't know, Santander, IBM, BBA, whatever, right? NVIDIA, whatever you want. You have stock number 1, stock number 2, 3, 4, 5. And then you have, let's say, a budget of 1,000 euros. You need to determine how much of your budget you want to allocate on each of those assets. I want to put a fraction of those 1,000 on asset 1. I'm going to call it omega 1, omega 2, up to omega 5. And there is a clear constraint in this analysis. I understand that you don't want to work with a particular amount. Whatever is your budget, we work in normalized terms. We work with fractions. All right. Then you need to consider what we call the budget constraint. The sum of all your wages need to be equal to
1.
all what you spend in your portfolio needs to go wherever is the total of the portfolio. And now, those weights can be positive. That means a buying position. So remember, that means that you go long on asset I, or can be negative. And that means that you short sell, you are selling your portfolio, that particular asset, or that you are going short. Now, the question would be, is short selling allowed or not? If short selling is allowed, we don't need to put this constraint. Omegas can be positive or negative. But if short selling is not allowed, we need to restrict, we need to constrain our analysis, we need to restrict it to omegas that need to be greater or equal to 0.
But if I have a short-only portfolio, it's not gonna sum up with. Okay, it's like the absolute value of those needs to be. That some of the absolute values of those have to be.
You can take positive fractions of your wealth, and that's what you expect. That's a buy. You are buying, but you may be able to short sell. That means a negative fraction. So the question is, for certain investors, that's a possibility. Probably not for you and for me, but for certain investors, that's a possibility. So, guys, I need to warn this particularity of this analysis. These omega fractions are most of the time positive, but they could be negative if we allow for short selling.
That's like your budget constraint, right?
That's the buy. This is the buy constraint.
So the mega is
How much of your wealth you put, of your budget, you put on a particular stock. 20%. I allocate 16% of my budget on NVIDIA. That's omega 1.
So the negative, that's,
Negative is you are so selling that particular asset. And you can do that in order to get money, in order to say, okay, I am going to invest over 1,000.
you mean short sell as an investment strategy, right?
Exactly. So omegas, the omegas can be negative. All right, so what is the point here? We are going to have an expected return of the portfolio. We have K assets. We are allocating a fraction omega I on each of them. The mean of the portfolio, the expected return of the portfolio, is the weighted sum of the individual means. That can be written in 3 ways, depending on the degree of mathematical sophistication you like. So, first level, the children, omega 1 times mu 1 plus omega 2 times plus omega k times mu k. Next level, that's the sum of the omegas times mu's. The people in the US just call the S notation, right? The sigma notation, the sum notation. But in the top level, you like things much more sophisticated, much more elegant, and much more useful if you are going to work with a computer. And that's the surprise, the benefit from this notation. If you like to work with computers, the expected length of portfolio can be written as what is called the inner product of two vectors. I have a vector A, B, C, and another vector D, F, G, and I can do the cross product, the sum of the cross products by transposing this vector. So this column vector becomes a row vector times the column vector. So the three entries are going to be multiplied this by this one, this by this one, and this by this one. And I can take advantage of the matrix algebra to do this operation. Now, which one you prefer depends on your background entirely. People with a decent background in mathematics should feel comfortable with that. In economics, sorry guys, no excuse. We have that background. An engineer has a background. But people who doesn't have a decent background, all right, think in this sense. This is much more compact. This is simpler. And more importantly, this is the way a computer will handle the problem. Do you really think that a computer is going to take this guy, times this guy, plus this guy? No, the computer will take a raw vector, transpose it, and multiply the other array. And we are going to do that in this step. So I need to make clear this algebraic transformation. That's for the mean. Then we say that the other input, the other characteristic of the portfolio that is relevant for us is the variance of the portfolio. The variance of the portfolio is much more complicated to express because it's like the sum of it's the square of a sum. You have two elements in a sum, you do a square, what happens? You will have a squared plus b squared, right? You will have all the squares of the elements, but then you have something like a 2 times a cross product. If you put more elements, things can become much more complicated. This is exploding. The number of elements is quickly exploding because of this combination of factors. You will have all the squares of the individual elements, and then you have all the 2 times all the cross products. 2a times c, 2 times bc. And this is growing exponentially fast. This can be written as the double summation of the weight that you allocate on asset I, the weight that you allocate on asset J, and the covariance between Y and J, noticing that when I and J refers to the same asset, the covariance between asset I and asset I is the variance. So it becomes much more complicated because we have all these cross products that depend on individual variances and cross products related to covariances. So this double summation, once again, can be written in a very simple way if you introduce matrix notation. This object, which is super complicated, is equivalent to take the covariance matrix that we saw this before, and we are going to pre-multiply, so this is a k by k matrix, we are going to pre-multiply by the transpose of the vector of weights, and post-multiply by the vector of weights. This is called in mathematics a quadratic form. Involves these summations, and you see what happens. This k by k dimensions agree, this k by k dimensions agree, you will end up with a value which is 1 by 1, and scalar. This operation produces a scalar, a number, which is the variance of the portfolio. And as we explained in the first chapter, variance is a bad thing for us because the units, we dislike it. The units are written as a square. So we are going to work with volatilities, which are the square root of the variance. All right? So, that sounds complicated. It is not. I'm gonna use, like the children, and they use this Excel with colors and things, because you probably are like a story like, oh my God, I hate math. I didn't know that economics and finance was so much about mathematics. Guys, it's the way it is. I'm gonna use this workshop in variance 5 that is uploaded in app. Let's practice the idea of working with vectors. So imagine that we have an array, we are going to work with arrays in which we will have, let's put it in context, in the mean variance setting for the applied work, we need to characterize two objects. One is a column vector with expected returns. So here we have three types of assets. We have treasury bonds, corporate bonds, and stocks. Stocks are more profitable on average, 9%. Corporate bonds are much more conservative, is 2.10%, and treasury bonds, notes, those are, very, very kind of conservative, just 0.6. But look at the volatilities. Yeah, this is the trade-off. This thing that is super profitable at the same time is the, well, who knows, 9% on average, 20% volatility a year. This will be the market. If you go to corporate bonds, that investment is much more conservative, but look, half of the total risk. And if you go into the treasury bonds, that's way lower in the support.
Those are the average return.
That's the average return.
0.6%.
Yeah, it's not real. Because we will work in the homework, we'll give you real data. Because you like it.
T-bills don't pay that, but I mean, like, I know it's not real, but it's
It's
not
not
so
real.
far off.
Exactly.
Like, T-bills are.
It's too low, it's too little. We already saw that here, guys. Well observed, by the way. Indeed, if you see real numbers, it should be more like this, right? Volatility of US 10-year treasury bonds is around 8%. We get something like, I don't know, 4 point something. So those numbers are not real. But it's an old exercise. It's been very long with me. I like it even though I know it's not real. I will give you real data because the point is how you get these estimations. For instance, based on historical data. And I know, maybe that's not all the idea, but let's say that this is how you go anyway. And then we have the covariance matrix. These elements here are variances. Those annual volatilities are the square root of these guys. If I go there and I type the square root of this guy, I get this number. I put it in percentage because now it's a return, right? Variance, I cannot give it meaning and interpretation. It's a number. But if you take the square root of this guy, you get this volatility. You take the square root of this guy, you get that volatility. 0.10, you put it in percentage, that's 10.10% annually. So this is the objects we need to work. A matrix, because we are working with three classes of assets. This is a 3x3 matrix and a 3x1 column vector. And that is going to involve a number of mixed operations. Now, as I said, you guys can think of the expected return of a portfolio in these simple terms, right? And that's fine, that's absolutely fine. This is fine as well, but this is how we can work in Excel. Particularly something with Excel that naturally works with arrays. So we have a special type of functions in Excel which are called array functions. An ordinary function in Excel produces an output that goes into a single cell. This is called function. But certain type of functions produces an array, a range of values that go into a cell. Those functions are called array functions. And Excel is equipped with array functions to deal with matrix operations. You can transpose, you can compute the inverse of a matrix, you can do the product of a matrix using the rules of matrix algebra. So, first thing that we are going to learn to do is how to work with the matrix algebra in Excel. We can compute the expected return of a portfolio by doing the inner product. Inner product is you take two vectors, the original position is the column vector position. You rotate one of them, so this is this is going to be 1 by 4, the other is 4 by 1. And now, in matrix algebra, this vector and this vector are said to be conformable. That means that this dimension and this. So you can do certain operations. The inner product is taking this element times this element, plus this element times this element, plus this element times this element, plus this element times this element. This is very complicated because it's doing the cross product that we did, remember, with some product. We can do some product or using matrix notation. And there is a function that is called matrix multiplication. This is meant to do the operation of the arrays. As long as the matrices are conformable, you need to fulfill the conditions of matrix algebra. You can multiply a random matrix A times a random matrix B. You can multiply this matrix, a vector is a matrix, a particular piece of a matrix. You can multiply this vector and this vector because the dimensions are given. So, matrix multiplication of array number 1 times array number 2. That's going to produce the inner product of two vectors, but for instance, would be useful for us to compute the expected return of a portfolio. Enter. We get it. Okay? Now, we can transpose. Another array function important for us is the transpose. We have a row vector, which is 1 by 4. We want to transpose it. We want to express this element in a 4 by 1 vector. So what we need to do is the following. This is the array that we want to transpose. I know it's 1 by 4. I can see it. So manually, and this is the limitation of Excel, manually I need to underline the area, a 4 by 1 area, where this vector is going to be placed.
Yeah, I can do it in the symbols here.
Huh?
I
And you get four observations?
go to 4 to the
Well, they are changing those things. I doubt it. Let me do it first correctly and check. What you are saying, Jesus. But we underline the 4 lines. We type the equal sign. We go with transpose, which is fairly conspired, right? And then we take the 1 by 4 array. Enter. And then we have the 1, 2, 3, 4 array transpose. Let me check what Jesus says, because this is no, because it's true, it's maybe true. Just let me say. Good.
I don't know if you noticed, but the 4 cells are like,
Yeah.
la fórmula.
You don't,
Like, they are, if you click on them here, like, o sea, como que te las marca, como si te las hubieran
with an array, meaning this is a pack. That's what we can together.
No, but if you add another number, like 1, 2, 3, 4, 5, the formula is going to
It allows you to do
add,
that.
yeah, to add it, but in the other. Si son fórmulas corridas hacia abajo.
Ahí se mueve.
Por eso están por
They
eso-
are data no so long, no so far away. You have to play the array function was executed with Control Shift Enter. So pressing a special combination of keys, and right now not even pressing that, not even underlying the area, which is cool. The other guys, it's been so many years underlying the area that it will still underline, right? So practice that, guys. We have the 5, 6, 7, which is a column vector. We can transpose that right away.
So before, how do you have to do before?
Uh,
How do you have to do before?
You need to underline the area, and then type transpose, and then Control Shift Enter. It was a combination of three keys in order to invoke the array function. Alright, so right now will be like a transpose of 5, 6, 7, 8, right? So we can do product of vectors, we can transpose, we can multiply two vectors. If the first vector is a column vector and the second vector is a row vector, this produces the outer product of two vectors. The inner product is a scalar, the outer product is a matrix. 4 by 1, 1 by 4, agreement in between the 1 and 1, and we get something that has dimension 4 by 4. So I underline the area in which I want to place my 4 by 4 matrix. Let me check the source point. It works also with. So we go with matrix multiplication of the column vector and the row vector. And pressing enter. Yes. Is producing the matrix. So no need to know no need to underline the anymore. You can make the product of two matrices as long as they are conformable. 4 by 4 times a 4 by 4 matrix can be multiplied, no problem. So we do that operation as well. And we did this. And the last important array function in the matrix world is the inverse. Inverse is very high-tech. Inverse is very complicated. So we go with inverse of the matrix, a 4 by 4 matrix, and now if this matrix can be inverted, not all matrices can be inverted. If this matrix has no zero determinant, we
Yeah, because you're lacking an N on the beginning.
inverse, right?
It's
It's inverse, matrix inverse.
Correct. Matrix inverse. So we invert the matrix. There we go. This matrix times this matrix should give us the identity matrix. A vector with zeros in the diagonal and ones. Roughly speaking, it's going to be a sort of rounding error. So let me see if we do the matrix multiplication of the original matrix times the inverse. We get, you see, the ones, and then something like a 0, 15 zeros should be exactly 0, but Excel is doing a kind of rounding error in this context.
Do you go back to the formula that I last one?
Which one?
This. No,
This is-
the.
For inverse. Okay?
It's funny because, for example, when I did the multiplication between the matrix and the inverse, it says 1 minus 0, 0, minus 2 to 10 to the power of minus 16. So it's funny
To
because,
the power of minus 16 is 15 zeros.
yeah,
And
but
this is what is called se llama en Spanish we call it el problema del punto flotante, the floating point, which means cell has problem to deal with very small. Every computer has problem to deal with very close numbers, which should be 0, and he deals them as if they were not 0. If you say, is this 0? Excel will tell you it's not 0. It's not, but it's all right because they are kind of rounding error, internal rounding error.
But what I said is funny because it tells me in the second column, it says minus 0, 1, minus 0, minus 0.
Minus 0.
Minus 0. Minus 0.
Sign is 0, but there is negative sign.
Yes.
I have positive 0, which probably is not 0 either. It's 0,
Yeah.
and he treats this as a 0. But see here we have minus 0, 16 zeros, and then a 2. If you ask, you make a condition and say, is this 0, right? If this is 0,
It's going to say false.
give me 1, give me is 0, right? And otherwise, tell me it is not zero. He said me, it is not zero. That's an error. That's a floating error. Okay, guys? So, what is the mean variance analysis about? We want to determine the optimal composition of the portfolio. And because we have two dimensions, being optimal means that the problem can be stated in two different ways. We have the volatility of the portfolio in that axis, we have the mean return of the portfolio in that axis, and we have something that is dominated by this external envelope, and any portfolio below is not efficient. We don't want to be there. We want to determine the composition of the optimal portfolio. Give me the recipe, how much I need to invest in each of the stocks in order to lie on the envelope. And we have two dimensions. So depending on which dimension you choose, you set the problem one way or in another. So, if we select a level of returns, I want this level of return, then all these portfolios have the same level of return I'm looking for, but they are efficient. And this is the optimal portfolio. This is the one that will have the minimum variance possible. For instance, when compared to this one. That one has a suboptimal level of volatility. This is one way of stating the problem. We want to minimize the volatility. We want to choose omega optimally such that we minimize the volatility of the portfolio, because that's a function of your weights subject to constraints. First constraint, we want the returns of a portfolio to be equal to a certain level that we have chosen. That level that we precise. This is I'm going to call it the target constraint. You identify your portfolio by choosing how much return you want. I want an efficient portfolio with 6% annual. Then we need to minimize the level of volatility. And we need to add another constraint, always, which is the sum of the weights needs to be equal to 1. And we are going to call this additional constraint as the budget constraint. That's one way to select the problem. The other way is just the other way around. We can determine a level of volatility, so all those portfolios have the same level of volatility, but that's the one that achieves the maximum level of return. So we can, as an alternative, we can choose a optimization problem in terms of I want to determine the optimal composition of the portfolio in order to, I want to maximize the expected return of the portfolio, because that's a function of the omegas. If you want to do that, you need to subject to, and then we put a target. And here the target, which is less natural, but the target is I want the volatility of my portfolio to be certain target, certain objective, given that I want that, I want the maximum return, and of course the budget constraint. I want the sum of all those weights to be equal to 1. So we can state two alternative problems that characterize optimality, that characterize efficiency. You fix one dimension, and then you go optimal in the other dimension. If you fix volatility, going optimal in the other dimension is maximizing return. And if you fix return, going optimal in the other dimension means minimizing volatility. We will always have to put the final constraint. The sum of weights needs to be equal to 1. And then we need to select the constraint.
But wasn't there a way of like finding the tangent of that group in which we had the best portfolio with the less risk?
Given what? Then there is a third problem. Excuse if I don't get you wrong, which is you want the optimal portfolio with the smallest variance possible.
Yeah, that was the first point of the efficiency.
So there is a third problem in this context, which is identifying this point. This is called the global minimum variance portfolio. Is the portfolio with the smallest variance among all the assets in the efficient frontier. The problem there, the global minimum variance portfolio, is I want to determine the composition of the optimal portfolio to minimize the variance of my portfolio subject to binding constraint. The sum of the weights needs to be equal to 1. End of the story. No further constraint. I just want to determine the efficient portfolio with the smallest variance, and I don't care about how much I get. My objective here is having the smallest variance as possible. So those are the 3 optimization problems that we can set in this context, and that will determine the composition of the portfolio. And in order to do that, we need to use a kind of old mathematical algebra. We are not going to use that. Or computers in the 21st century are available for everyone, equipped with an optimization, and we just use it this morning. Solver is going to solve this problem for us. So guys, we have like 30 minutes. Would you like to do an optimization problem?
Solver.
Solver. Let's go. So, we have 3 assets in the Excel file. I want to characterize what we call the efficient, first I want to characterize the investment portfolio. And I'm going to use that involves the formulas, the algebra. And when I have that, everything's going to be very simple later. This, I don't need to copy, because if you go to the Excel file, you go to workshop 1, we have this data here. This is the input data, so what I'm going to do is making a copy. Okay, that was the original data, now I have a copy. Nice. I take it, click on it, control, and you drag it. And then you are making a perfect copy of that file, okay? Okay, I'm gonna say in-class solution to this file, in-class solution. Alright guys, let's simulate portfolios. This guy is the expected return vector. We are going to do a lot of operations with expected return. I need to type D3 to D5 all the time. And that's going to be kind of waste of time, conversion. Yes, so instead of calling D3 to D5, we underline the area, be careful. We underline D3 to D5 and go up here and let's call it SRET, expected return. Okay, hit enter. And if I underline this guy is going to be expected return. And I can refer to this guy as expected return all the time. And this is the covariance matrix. Symbolically, we call it omega. So I'm gonna call this covariance matrix. I underline the 3 by 3. I go up here, and we are gonna call it omega. And Excel doesn't distinguish between capital letter and small letters. I use capital letter because of so many years programming with languages that do distinguish things. And omega makes, to me, remind me that this is a matrix. All right, hit enter. Let's do some Monte Carlo analysis now. Let's make portfolios. Let's simulate portfolios. How many portfolios, guys?
1,000.
Why? It's going to be the computer, not us. 1,000, that's fine. Let's go for 1,000. Jesus, just nail it, right? Like I just nailed it, right? Jesus, 1,000. So bring it on. 1,000. Sequence, remember? Remember the Excel command? Sequence of 1,000. That's going to be the simulation number 1, simulation number 2. So we have 1,000 guys making non-educated decisions here. They are gonna make their mind, and they don't know. They don't know about market optimization, portfolios. Someone comes and says, I'm gonna go for treasury bonds. I'm gonna go for the weight on treasury bonds. I'm gonna go for the weight on corporate bonds. And I'm gonna go for the weight on stocks. Okay, I'm gonna center this thing. I give it black, so bold letters, you see it more clearly. Those are the weights. I'm gonna make an additional column here. This is not necessary, but just to check things. This is the sum of weights. And if everything is fine, sum of weights should be equal to 1, right? All right, let's go for a guy that wants to invest in treasury bonds. This is a random guy. This guy wakes up this morning and says, I want to invest a random number between 0 and 1. So this is a long or short position. This guy goes for a 0.22, long or short? Long position. He wants to buy. I'm going to give it percentage, okay? Percentage sign, a couple of decimals. He wants to buy 22% of his budget on treasury bonds. I center.
We just wrote.
Huh?
Sí, random, sorry.
It's random. It's going to change all the time. Next guy, the same guy for the corporate bonds. This guy is going to say, I'm going to go for 92% massive investment on corporate bonds. I really like those corporate bonds. Now, what happens with the stocks?
He has to short the stocks we want.
Because the constraint needs to be binding. If we impose the condition that the sum of weights equals 1, we lost 1 degree of freedom. You can freely choose the position in 2 assets, but the third one is implied by the remaining of your portfolio goes into that one. So for instance, for this guy, going to a 92% on corporate bonds and 64 on treasury bond, he needs to go short on stocks. So we are gonna go for stocks, and we are gonna use in this simulation stocks to close, to make the one binding condition active. So this is gonna be 1 minus the sum of those weights. So this guy is taking 71% buying treasury bonds, 96% buying corporate bonds, and that's a superposition. So where he gets the money from selling stocks in a 67%. And of course, if everything is fine, the sum of the 3 weights needs to add up 100%. It's a good idea what this guy is doing. What do you think?
No.
Why not? Vivian.
Because I think, because if lower the stocks, so the return will be lower.
If you want to go short, you are selling, you want to sell the expensive, you want to buy cheap, sell expensive. This guy is buying expensive you see, is taking the opposite position. This guy is betting that the market is going to lose 9%. He will losing and expecting 9% because he's selling the stocks. So he will lose 9% in order to buy things that give 2% or 0.60%. The total expectation of this portfolio is going to be negative. Press F9. What about this guy? Is this guy doing something sound? Yeah, he's buying he's diversified. We may say maybe it's not the best thing, but it's not so stupid as the guy that is so selling the stock to buy corporate bonds. People do the opposite. They go and borrow at a 2% to buy things that yield 9% to earn the difference of 7%. This guy is going to lose that 7%. Okay? We underline the 4 lines. We are next together a column vector that has the 1,000. We look for the bottom right corner, the shape of the mouse changes, double click, we have 1,000 portfolios now. Okay? We want to characterize 2 things of this portfolio. And this is the mean variance setting. We need to care nothing else but expected return and variance. So let me put it for reasons in order to make the graph. Let me change the order. That's going to be the variance of the portfolio. That's going to be my first column here, G. It's going to be that's going to be the variance. Okay? Next, I'm going to put the volatility. And this is very simple. Column H is just the square root of column G. And then the expected return. So that's going to be the mean, right, of the portfolio. And this is very easy to compute. That's going to be the mean return in your life, mean. Variance, volatility, mean. We want to make them, I put it in this order, because the plot that we want to plot is return versus volatility. And in Excel, this goes like volatility mean. First column is X's, second column is Y. So I'm picking up this order in order to make the graph more naturally. So let's start from simple to difficult. Very simple, the expected return. I go to the mean. We want to do the matrix multiplication of this vector times this vector, right? We want to do this guy times this guy plus this guy times this guy plus this guy times this guy. So I'm going to use the matrix multiplication. So we want to have one vector transpose and the other in the column format. We have the omegas already transposed. Omega is kind of transposed already. Whereas the mean vector of the individual stocks is in column vector. So we can take advantage of that position to make the operation. The matrix multiplication of these weights squeeze a little bit. Okay, there. The matrix multiplication of this array times the expected return vector, right? This operation produces the expected return of the portfolio. You guys all see it. I don't want that anyone is lost at this point. It's very simple what we are doing. I'm taking each of the weights times the expected return. As I said, this can be very complicated, but if we take advantage of the matrix algebra, this is super simple, super straightforward. So I presented, and that number is a percentage, so I'm going to emphasize this idea. That's a percentage, couple of decimal. This guy that is taking a short position in stocks of 18%, he's investing much more to sell bond, and yet, even just investing 18% in stocks, that minus 9% gives a loss. He's expecting to lose 0.17%. No rational investor will do this thing. We can lose money in the market. Of course, we are investing in the market, sometimes win, sometimes lose. I will never invest in the market expecting ex ante to lose. This guy is irrational. Irrational is the word we use in economics to mean stupid, idiot, crazy. Don't do that. You know you are going to lose money, and yet you go. What is wrong with you? Yeah, he's going to lose 0.17%. Okay, reset. Let's look for this new guy, 3.27. This guy is making a portfolio. That's a portfolio. What we don't know is whether this is efficient. But 3.27% looks fine a priori. Variance. This is the toughest thing we're going to do today. Variance is the most complicated object because it involves three things. Where do I have the So we need variance of the portfolio is, look at the recipe, the mathematical recipe, your weights transpose. So that's a 1 by k vector. Then you need to multiply the omega matrix with the covariances. This is a k by k matrix. As you see the agreement, because these two dimensions are the same, this is conformable. That's agreed with matrix algebra. And then you need to post-multiply this thing in order to produce the quadratic form. And this is a k by 1 vector. So we have this agreement. Now, we are going to multiply matrices, we are going to multiply arrays using matrix multiplication. The problem with matrix multiplication is that it only allows us to multiply two matrices at once. We need to do an operation involving three matrices, or three arrays if you prefer it. So we are going to do things in a much more complicated way. I'm going to take this omega. So I'm going to take the omega prime, and then we are going to post multiply it, and here the order in the array function is very important because we are letting know Excel in which order the product needs to be done. And you know that in the matrix world, A times B is not the same as B times A. The commutative property does not hold in the matrix world. It holds in the scalar world, but not in the matrix world. So the order is important, and the order is preserved in Excel. I'm going to take that matrix and then post multiply by omega. And this is what I can do. That's going to be my first matrix. And then I'm going to nest this matrix multiplication into another matrix multiplication. And this outer matrix multiplication will take as first input this product. And then we post multiply it by the other guy, by omega. Now we need to be careful because this is the formula. That's what the theory tells me that I need to do. And another different thing is what we have in the Excel file. I need to accommodate my Excel file to do this operation. So in my Excel file, what we have is omega transpose. This is already, right? This is a 1 by k vector. We have that because this is this array. I have it right there. We have omega, that's a k by k vector. And then we need to multiply by what is called omega, which in the mathematics, in the theory, is a column vector. And we have here omega in a row format. So we need to transpose it. Alright? So let's go carefully, okay? Because you see, it's a little bit complicated, but because we know the plan, we have a plan, we will not get lost. So we go. I'm going to assume it, okay? So for the variance, matrix multiplication. I check the recipe. The mathematical formula tells me, pick up the transpose form of your weighted vectors. It should have a row form. Yes, I have that. This is this guy, this guy, this guy. All right, fine. Second argument of the matrix multiplication operation, omega. So I'm going to type omega, and you see that omega is automatically underlined. We are fine. This operation can be done, but this will produce a 1 by k vector. Okay, so we are not going to press enter. We don't want that vector popping up. That's part of the story. And now go. In the outer side, we go for another matrix multiplication. I open parentheses, and now it's asking for 2 inputs. Okay, my first input is going to be all this. So I go to the end, and I put semicolon. And now you see the outer matrix multiplication is asking for the second array. It's recognizing the pattern. You have all that thing there. Nice. What next? The theory tells me I need to post-multiply by omega, omega being a k by 1 vector of weights. But we don't have a k by 1 vector of weights. We have a row vector. So in order to accommodate what I have in my book to what the theory tells me, we need to transpose the weights that we have here. This guy needs to post-multiply in this second matrix multiplication. So I close this parenthesis and I close this parenthesis. Take your time, guys. This is important. It's complicated. It's a complicated structure, but we are taking at the level of Excel. Beyond this, there is just Visual Basic programming. This is like the most advanced thing that we can think of. We are going to optimize involving matrix operations. This is you are going to abound in Excel. There can be done much more complicated things, but those involve Visual Basic programming. So I repeat what we've done. First, we compute inside this matrix multiplication. We take what is symbolically represented as the transpose of omega in the theory, because remember, vectors in theory come as a columns naturally. We want the row vector. Yes, we have that. Times the matrix of covariances. So this thing is done internally up here. And then in a second matrix multiplication, we are nesting this matrix multiplication into another, taking the result of this matrix multiplication as an input, and post-multiplying by, the theory tells me, a column vector of weights. We don't have the column vector of weights. We do the operation through using the transpose. Now, if everything is fine, that should give me a number. So, if it's a number, and that's a variance, I will not use the percentage sign. I'm using the percentage sign whenever we want to emphasize this is a percentage. So with the mean return, that's a percentage. This is return squared. That number means nothing for us. So I'm going to take the square root of that guy, and this is in the same units as the return. Not this, this. So I go with the percentage, a couple of decimals. I'm going to center everything. And if you are ready, I launch the whole thing down. If you are ready, copy, paste down, and we have volatility and mean. And now, I'm gonna save this thing. Okay. And now that we have this thing, we can plot and take a look how the investment of these stocks and guys look like in the plane of volatility, risk, and expected return, profitability. So I take volatility and mean, okay, and I select this as a kind of rows, control, shift, down key, and we select all that range. Insert, recommended chart, can you see it? It's kind of mirroring because the stock volatility is creating something that we don't want to go there. But the bad investors, the ones that are short selling the stock, will go down into the negative region. This is the mean variance space. Okay?
How do we get the low minimum variance portfolio?
Now you need to go optimal. So far, this is descriptive analysis. This is just characterizing the investment. These people, all these guys that are losing money, those are the ones that only short sell the stock.
The noisy trader.
Well, all of them are noisy traders. All of them. Some of them are particularly bad noise traders. Some of them are not sophisticated. And these up here in the envelope, those are lucky guesser noise traders. Without knowing what we're doing, they were able to get the maximum combination of the efficient portfolio.
The graphic for mean and what else?
Standard deviation, mean. So the order in Excel is important because Excel, the way it plots is first the x-axis, next the y-axis. So this is the, we can call it the mean variance universe, right? AKA the investment set.
And the type of graph you're using? What type of graph are you using? Scatter?
It's a scatter plot. If we press F9, this is being, because we have 1,000, you see Monte Carlo, right? It allows us to see that this mean variance combination is up there. 8 minutes to go, guys. If you're not tired, we do optimization. We do one single optimization. You are not too tired. Not, if not on Monday, or if not, it will be on Monday. I don't want to push you too much. It's been 6 hours teaching today. If you want, you see, we do one optimization.
That's all they profit. For me, the nice hour of class.
I know. That's why I'm asking. Normal circumstances would be, let's go for it. Questions, guys? This is what we are going to do next day, doing the optimization. This is mean balance. Now the question will be, we are gonna, and you guess what we are gonna do? We are going into the data solver, and we are gonna define. We are gonna define a program. Let's do it. You don't know. I don't know. I don't know what is doing that, but reset. Okay, so that's what we're gonna do. I'm gonna start the solver, and then we're gonna go and say, what do you prefer? The idea of optimizing, giving some target in the volatility, some target in the mean.
The mean.
You fix that's what we're gonna do, and this will determine the composition. 5 minutes, guys. It will not take you much to take us more. Just one single optimization. So you want, let's define the problem in which terms?
Let's start with the mean. So
You
let's
want-
maximize the mean.
Maximize the mean given volatility level.
Uh-huh.
So in order to do that, we need to take a look at what volatility is, right? Volatility, it goes something between 4-5% to 20-25%. So don't ask me for 2%. It will not be feasible. Nothing here has so small volatility. We are talking about 5%. Which level of volatility would you want into your portfolio?
10 is with
10%. So see, in the 10%, he, Jose Daniel, wants a 10% return. Okay, let's go there. I'm gonna make the calculator. So I'm gonna take these guys, I'm gonna copy paste this structure. Because this can be recycled. All the formulas are there, no problem, no fear. I'm gonna take there, I'm gonna take here my calculator, my portfolio calculator, okay? And we saw. And then I'm gonna take those random portfolios, blah, 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 everything here, and we are gonna copy paste it. No fear. Those weights are randomly generated, fine, the sum equals 100, then we have the variance, we have the volatility, we have the mean. Now we need to add one column. That's gonna be the target. So you want target volatility, right? Our target is gonna be in terms of volatility. I'm gonna put it like this because this is special, right? That's gonna be a kind of condition. And you want how much?
10%.
10%. Like this. Now, go to solver. Data. When you press solver, everything seems to crash, I don't know why. If that happens, say reset all. That may happen. So press reset all and we start from scratch. Okay? Now, very important thing. We want to consider short selling or not. That's super important. And this, guys, as I said this morning, unfortunately, solver has this tip. If we leave it, we are forbidden short selling. We want to forbid short selling. The exam will be completely clear. I need to state that short selling is allowed. Short selling is not allowed. So let's say short selling is allowed. Then you need to unclick. You allow negative positions. Then that's short selling is not allowed. Then I need to click that constraint. So short selling is a possibility. We go like that. All right. First thing, what is our objective? What we want to do?
Maximize utility.
Maximize is not utility, expected return. Where is expected return? Is here, right? And we want to maximize that. That's okay. By changing what?
By changing the weights.
This weight in my calculator, this weight in my calculator, this weight in my calculator. Okay? Look short. So first of all, we want to select the objective. We want to maximize that guy by changing the 3 weights. Okay? And now, and this is super cool. This is super cool. We need to do constraint optimization, subject to the constraints. So we are now going to add a constraint. We go to add. Now, first constraint. We want the volatility, which is here, right? We want the volatility to be equal to the target, 10%. Okay. And now we have that constraint. Something else?
Yeah, that the sum of weights has to be 100%.
Super important, guys. Another common mistake in exams. People are under pressure, people running, people not so familiar. Sorry to mention. What we are doing, forget the constraint equal to 1. We are gonna add the sum, which is here. Right now it's 100. Yeah, but you need to bind this condition. It needs to be exactly. Excel will look for many portfolios. This condition needs to be binding. So we need to remind Excel in each iteration that sum needs to equal to 1. Okay? Okay. We are ready. Take a look, we are maximizing expected return by changing the weights, subject to the budget constraint, subject to the target constraint that Jose Daniel wants, 10% volatility. Then we go for solve. Excel makes its magic, says solver for a solution, bring it on. Now we need to check. The check was target volatility was 10%. This is 10% volatility. The composition of that portfolio has a 100% total. This is the efficient portfolio. If you want to achieve 10% volatility, that will produce a 4.48% return, expected return, and the recipe to do that is around 41% on treasury bonds, 15%, nearly 16% on corporate bonds, and 43%, most of your investment goes to stocks. Error. Reset everything. Reset Jesus. Let's see, checks. How many problems? Problems, pen 0, problems.